we have been looking at the decomposition of a Hermitian matrix as the sum of rank 1 matrices. Let us recall some of the things that we obtained in this context. So, we shall consider a matrix A which is in Hn, that is A is Hermitian. We want to express this as the sum of rank 1 matrices. Now, we will follow the notation. Let us recall, if U and V are in Cn, then we define V tensor U to be the matrix U V star. Notice that this is an n by n matrix. This is an n by n matrix, and if we now look at this matrix and look at its Hermitian conjugate, it is U V star star, which is V star star into U star. So, when you take transport of a product, the product of the transpose in the reverse order. When you take the Hermitian conjugate of a product, the products come in the reverse order, but V star star is V. So, it is V U star. So, we have this notation that V cross U is equal to U V star star, which is V star star into U star is equal to V U star. Now, we have this tensor notation. With this notation, we shall particularly look at the idea of taking the tensor product of a vector with itself, then we get U cross U as U U star, and then U U star, since U equal to V above, is equal to U U star, which is U tensor U, and therefore, U tensor U is a Hermitian matrix. So, U tensor U is in Hn, it is a Hermitian matrix, that is a Hermitian matrix for every U in Cn. For example, if U equal to say 1 I, then U tensor U is equal to U U star. U is 1 I, U star is the transpose conjugate. So, it is 1 minus I. So, when you take the product, you get 1 minus I and minus I squared, which is 1, and which is a Hermitian matrix, which is a Hermitian matrix. So, if you take a vector in Cn and take the tensor product of the vector with itself, we get a Hermitian matrix. Now, we use this notation in the decomposition of the matrix. Recall, if A is a Hermitian matrix and its characteristic polynomial is lambda minus lambda 1 power a 1 etcetera, lambda minus lambda k power a k, our usual notations, where lambda 1, lambda 2, lambda k are the distinct eigenvalues of A, and a 1, a 2, a k are their algebraic multiplicities. Then we have W j, the null space of A minus lambda j I, which is the eigenspace corresponding to the eigenvalue lambda j, and the dimension of W j, which is the geometric multiplicity in the case of Hermitian matrices, will always be equal to the algebraic multiplicity. This is true for each j equal 1 2 k. So, for each one of the eigenvalues, the corresponding eigenspace has the same dimension as the algebraic multiplicity. Then we denoted by Bj an orthonormal basis for the eigenspace Wj. So, the superscript j says that it is a basis for the eigenspace Wj, and the subscript is the index of the basis vector. This is the first basis vector phi j 1, phi j 2 the second basis vector, phi j aj is the ajth basis vector for Wj. Then the union of all these j equal to 1 to k is a basis for the whole space. And we saw that this matrix A, we have seen that A can be written as the following sum. What is that sum? For each one of these eigenvalues and eigenspace, we look at first the Bj basis, there are Aj of them. For each one of these vectors, we construct the tensor product. So, we construct phi j r tensored with phi j r, and this is going to be a matrix as observed above. This is going to be an n by n matrix, and since it is a tensor product of a vector with itself, it is going to be a Hermitian matrix, and so that is a Hermitian matrix of order n by n, and it is multiplied by the corresponding eigenvalue j, and we look at this sum from r equal to 1 to a j. That is, for each one of these basis vectors in the Bj basis or the basis for Wj, we look at the tensor product. Note that this is an orthonormal basis in addition. Now, we do this for every one of the eigenvalues. So, j equal to 1 to k. So, totally we get a 1 plus a 2 plus a k n terms. So, note that phi j r is an n by n Hermitian matrix of rank 1. Thus, we have expressed the matrix A as the sum of matrices of rank 1. In particular, if 0 is an eigenvalue of multiplicity a k, say we call the kth eigenvalue as 0, then that is we say lambda k equal to 0, then we know that the null space of a minus the corresponding eigenvalue is 0. So, a minus 0 I, which is the same as null space of A, must have dimension same as a k, but we know that the dimension of the null space of A is nu A. Therefore, the nullity must be equal to a k. So, suppose we have 0 as an eigenvalue, then nu A must be equal to the algebraic and geometric multiplicity of this eigenvalue, and therefore, if you look at this sum, in this sum corresponding to the term lambda k, we will be multiplying by lambda k every one of these a k terms, but lambda k being 0, these terms will disappear, and hence the nu a terms corresponding to lambda k equal to 0 disappear in the above sum, and we get a equal to summation j equal to 1 to k minus 1 summation r equal to 1 to a j lambda j phi j r tensored with phi j r. Now, obviously, there are a 1 plus a 2 plus a k minus 1 which is n minus nu a. So, n minus nu a terms, but n minus nu a is the rank of the matrix. So, rho a terms. So, we have now each one of them is non-zero because these are orthonormal vectors, they are non-zero vectors and lambda j's are non-zero. So, thus we have a, we have decomposed a which is a Hermitian matrix as, and its rank is say rho a. So, its rank is rho a as the sum of rho a matrix, in fact rho a Hermitian matrices of rank 1. Each one of these terms is Hermitian. This is real because Hermitian matrices, the eigenvalues are real. So, when you multiply a Hermitian matrix by a real number, you get a Hermitian matrix. So, this whole quantity is a Hermitian matrix and therefore, the whole sum is the sum of Hermitian matrices and each has rank 1. So, thus we have seen that if you have a Hermitian matrix of rank rho, it can be split into the sum of rho 1 rank matrices. So, we will always reduce everything to 1 rank level. Let us look at some examples of this decomposition. So, let us look at the first example, a matrix which we have seen in the last lecture. You see that in all the above decompositions, in particular if A is real symmetric, we replace star by transpose everywhere, because conjugation does not give anything new in the real situation. So, this is a real symmetric matrix. And we have seen that in the previous lectures that its characteristic polynomial is lambda minus 2 squared into lambda minus 8, and therefore, it has 2 eigenvalues, it has 2 distinct eigenvalues. One of them is 2 and its multiplicity is 2 because we have lambda minus 2 squared. The second eigenvalue is 8 and its multiplicity is 1. So, we see therefore, that 0 is not an eigenvalue. Therefore, nullity is 0 and hence rank is 3. Since the rank is 3, we shall express A as the sum of 3 Hermitian matrices each of rank 1. How do we do this? For this we find the eigenspaces corresponding to these eigenvalues. The W1 is the null space corresponding to the eigenvalue 2. So, it is A minus 2i, and we have found in the last lecture that this consists of all vectors of the form alpha beta minus 2 alpha plus beta, where alpha and beta are real. And we found an orthonormal basis B1 orthonormal basis for W1, we found there will be two vectors phi 1 1 and phi 1 2. Because the multiplicity is 2 corresponding to the eigenvalue lambda 1, there will be phi 1 1 and phi 1 2. The phi 1 1 we found as 1 by root phi into 1 0 minus 2, and the other one we found as 1 by square root of 30 2 phi 1. These were the two orthonormal vectors which form a basis for the eigenspace corresponding to the eigenvalue lambda 1, which we have found in the previous lectures. Similarly, W 2 is the eigenspace corresponding to the eigenvalue 8. So, it is the null space of A minus 8 I, and we found this to be consisting of all vectors of the form x is equal to 2 gamma minus gamma gamma, where gamma is real, and there is going to be only one, the dimension being 1, there is going to be only one orthonormal basis for that, and this we found to be 2 minus 1 1 square root of 6. So, we have the three eigenvalues. Now, we and the one of them is repeated twice, 2 2 are the eigenvalues, and then the other eigenvalue is 8. Corresponding to them, we have the three eigenvectors. Recall that this corresponds to lambda 1 equal to 2, this also corresponds to lambda 1 equal to 2, and this corresponds to lambda 1 2 equal to 8. Now, we form the tensor products corresponding to each one of these eigenvectors. So, we first calculate phi 1 1 phi 1 1, and what is phi 1? It is just the 1 by root phi of 1 0 minus 2 times phi 1 transpose, which is 1 0 minus 2. Remember, everything is real here. So, we have to look at the transpose, and the matrix is 1 by phi. If we carry out the product, we get this matrix. We have done this in the previous lecture also. So, it is a simple matrix multiplication, we get this. Similarly, we look at the again the first eigenvalue itself, but look at its second eigenvector and take the Cartesian or the tensor product. It is 1 by root 30 into 2 phi 1 into the transpose of that, and when we carry out the multiplication, we get 1 by 30 into 4 10 2 10 25 5 2 5 1. Notice that this is a Hermitian or a real symmetric matrix. This is what we observed, that when you take Hermitian vector in C n and tensor with itself, we get a Hermitian matrix. In the real case, if we take a real vector and tensor it with itself, you get a real symmetric matrix. Again, this is a real symmetric matrix. And then finally, we look at the eigenvector corresponding to the second eigenvalue and do the tensor calculations with respect to that. It is 2 minus 1 1 1 by root 6 into 1 by root 6 the row vector 2 minus 1. When you carry out this product, we get 1 by 6 4 minus 2 2 minus 2 1 1 2 minus 1 1. Now, this corresponds to still the eigenvalue lambda 1 equal to 2, and this corresponds to the eigenvalue lambda 1 equal to 2, and the last one corresponds to lambda 2 equal to 8. Now, having constructed the tensor products of each one of these eigenvectors, we multiply them by the corresponding eigenvalues. So, we look at lambda 1, this phi 1 1 corresponds to eigenvalue 1 lambda 1, the phi 1 2 also corresponds to the eigenvalue lambda 1, and the phi 2 1 corresponds to the eigenvalue lambda 2. Lambda 1 is 2, lambda 1 is 2, lambda 2 is 8, and we have calculated the tensor products above. When we substitute all that, we get the summation as 2 by 5 0 minus 2 by 5 0 0 minus 4 by 5 0 8 by 5 plus 4 by 15 10 by 15 2 by 15 10 by 15 25 by 15 5 by 15 2 by 15 5 by 15 1 by 15. These are the two terms corresponding to the first eigenvalue. This is lambda 1, this is the term which is lambda 1 phi 1 1 phi 1 1 with the value lambda 1 equal to 2 and the phi 1 1 tensor phi 1 1 which we have found above. This is lambda 1 again with lambda 1 equal to 2, but phi 1 2 tensor phi 1 2, plus the next one is the other eigenvalue which is 16 by 3 minus 8 by 3, 8 by 3 minus 8 by 3, 4 by 3 minus 4 by 3, 8 by 3 minus 4 by 3, 4 by 3. Now, this is the term which is lambda 2 phi 2 1 tensor phi 2 1. And when we add all this, we get check. This is exactly adds up to the given matrix A. Now, notice that the first matrix we have here is of rank 1 because every row is a multiple of the first row. Similarly, the second matrix is a matrix of rank 1 because every row is a multiple of the third row, and the third matrix is a multiple of is a matrix of rank 1 because every row is a multiple of the third row. Observe also that each one of these is a Hermitian matrix. So, thus we have A as the sum of 3 Hermitian matrices of rank 1. Now, we have 3 of them because the rank of the matrix was 3. So, whenever you have rank row, you will have row matrices for which we will take of each of rank 1. Let us look at another example. A equal to 5, 10, 0, 10, 25, 5, 0, 5, 5. Now, if we calculate the characteristic polynomial, we get lambda minus 30 into lambda minus 5 into lambda. If you write down the determinant lambda I minus a and expand it, you will see that it can be factored as C A lambda equal to lambda minus 30 into lambda minus 5. So, what are the eigenvalues? Lambda 1 equal to 30, algebraic multiplicity 1, lambda 2 equal to 5, algebraic multiplicity is 1. Notice that lambda 3 is 0, which means that A has nullity 1, because lambda equal to 0 is an eigenvalue of multiplicity 1, and therefore, A has rank. The matrix is 3 by 3, nullity is 1. So, the rank is 3 minus 1, which is 2. So, A is real, symmetric and has rank 2, and therefore, we shall decompose this as the sum of, now since the rank is 2, even though the matrix is 3 by 3, since the rank is 2, we will decompose it as the sum of 2 Hermitian matrices, each of rank 1. Now, how do we do the decomposition? Once again we notice that as we observed at the beginning, when you do this decomposition, the terms in the decomposition corresponding to the eigenvalue 0 disappear because we multiply by the eigenvalue. So, we have to only concentrate on the non-zero eigenvalues. Therefore, we must look at only the null space of the first two eigenvalues. The first eigenvalue is just the null space of A minus 30 I, because the first eigenvalue was 30, and it can be shown, you can easily compute the solutions to be of the form 2 alpha 5 alpha 1, where alpha belongs to R, and therefore, an orthonormal basis for that is 1 by root 30 into 2 phi 1. So, that is the corresponding to lambda 1 equal to 30. Then we look at W 2, which is the null space of A minus the second eigenvalue, which is phi I. Now, it turns out we can verify that again this is consisting of all the vectors of this form, and the corresponding orthonormal eigenvector is 1 0 minus 2. Now, in the decomposition only the eigenvectors corresponding to the non-zero eigenvalues appear. So, we do not have to worry about W 3 because W 3 is the eigenspace corresponding to the eigenvalue 0. Now, we compute phi 1 tensor phi 1, which is 1 by root 30 into 2 phi 1 into 1 by root 3 into 2 phi 1, which we have calculated earlier in the previous example, and it turns out to be 1 by 30 4 10 2 10 25 5 2 5 1. This is the same as what was obtained in the previous example, and this corresponds to, we keep reminding that this corresponds to the eigenvalue 30. Similarly, the second eigenvalue we calculate the tensor phi 2 1 pi 2 1, which is 1 by root phi into 1 0 minus 2 into 1 by root phi into 1 0 minus 2. Again we have calculated this in the earlier example. It turns out to be 1 0 minus 2 0 0 0 minus 2 0 4, and this corresponds to the eigenvalue lambda at 2. Now, for the decomposition we have, therefore, how does the decomposition look like? We have to look at lambda 1, the tensor product of the eigenvectors must be multiplied by the corresponding eigenvalue, and there are only two non-zero ones here. Now, we have lambda 1 is 30, lambda 2 is 5. So, if we now multiply this by 30, this has to be multiplied by 30. So, the 1 by 30 and 30 get cancelled, we get 4 10 2 10 25 5 and 2 5 1, and then when we multiply this matrix by 5, the 1 by 5 gets cancelled, we get 1 0 minus 2 0 0 0 minus 2 0 4, and when we add, check that this is exactly equal to the given matrix here. Notice that each one of the matrices in the above sum is a Hermitian matrix, real symmetric in this case, and the first matrix is of rank 1 because every row is a multiple of the third row, and the second matrix is of rank 1 because every row is a multiple of the first row. So, therefore, we have expressed the A as the sum of two Hermitian matrices, in this case real symmetric matrices, because we are with real symmetric matrices each of rank 1. And why do we have only two matrices in the sum or two terms in the sum? It is because of rank 2. So, thus if you have a Hermitian matrix of rank rho, it can be always split into a sum of row terms of row matrices. Each matrix is Hermitian, each matrix is of rank 1. So, rank row matrix is the sum of row 1 rank matrices. So, the ranks can be split. This is the decomposition of a Hermitian matrix into rank 1 matrices, which we saw last time. These are the two examples. Now, we look at a special class of Hermitian matrices. Special class of Hermitian matrices. Now, first we looked at all n by n matrices, then we saw the various diagonalizability criteria, namely A m equal to G m, and then we found that there are matrices for which A m may not be equal to G m. Therefore, all n by n matrices are not diagonalizable. Then we looked at a special class of n by n matrices, namely Hermitian matrices, where diagonalizability was guaranteed. Now, inside this Hermitian matrix class, we are going to look at a special class. So, we had first the collection of all n by n matrices. In that we had the H n, the Hermitian matrices. Now, we are going to look at a subclass of the Hermitian matrices. Now, suppose I take any Hermitian matrix, we know that one of the fundamental properties of Hermitian matrices is that A x x is real for every x in C m. So, if you take even a complex matrix n by n and even a complex vector x, as long as the matrix is Hermitian, A x comma x always turns out to be real. This is a typical property of Hermitian matrices. So, for a Hermitian matrix, A x comma x is always real. However, it will happen in general that A x comma x is positive for some x, negative for some x, and of course, is obviously 0 for x equal to 0, x equal to 0 for x equal to theta n, and possibly for x not equal to theta n also. So, in general, even though we know that A x comma x is real, we cannot say precisely whether it is going to be positive or negative. For a general Hermitian matrix, it could turn out to be positive for some x, negative for some x, and 0 for some x. Now, we are going to look at a special subclass for which it always maintains the same sign. So, we look at those A which are Hermitian. Whenever I write A belongs to H n, what we mean is that A is a Hermitian matrix. So, we look at those A in H n for which A x comma x is always greater than or equal to 0 for every x in C m. Such matrices are called positive. We will write the formal definition, positive semi definite matrices. Now, we know that A x comma x is 0 when x is equal to theta n. We know A x comma x is equal to 0 when x is the 0 vector. Suppose in addition to being positive semi definite, we also have 0 the only vector for only for x equal to theta n, which means what? It is always greater than or equal to 0 and equal to 0 only for x equal to theta n. That is, a x comma x will be strictly positive for x not equal to. We say A is positive definite. So, we will write the formal definition. So, definition, first of all these notions of positive semi definite and positive definite we are introducing only for Hermitian matrix. So, a Hermitian matrix that is an n by n Hermitian matrix is said to be positive semi definite if a x comma x is greater than or equal to 0 for every x belonging to C n. If further a x comma x is strictly positive for every x not equal to theta n, x belong to C n, we say A is positive definite matrix. Analogously, we can define negative semi definite by replacing greater than or equal to 0 by less than or equal to 0 and negative definite by replacing greater than 0 by less than 0 above. So, we have the notions of positive semi definite matrices and positive definite matrices. What are the some important properties of such matrices? We are going to use all these properties eventually to analyze a general method of, I will write PSD for positive semi definite matrices. So, let A be a positive semi definite matrix. Now, we have seen that the notion of positive definiteness a priori assumes that it is a Hermitian matrix and therefore, all properties that we had for Hermitian matrices also hold for A, because A is positive semi definite. Recall our picture, the positive definite matrices are what are these? We are now looking at the positive semi definite matrices. They are sitting inside the Hn. So, whatever properties hold for Hn, hereditarily they hold for positive semi definite matrices. So, all the properties that we had for Hermitian matrices hold. What are some of the properties? Eigenvalues will be real, eigenvectors corresponding to distinct eigenvalues will be orthogonal, algebraic multiplicity will be equal to geometric multiplicity for all eigenvalues. The matrix, if it has rank row, can be decomposed in terms of row 1 rank matrices. All these properties will now sweepingly can be applied for positive semi definite. But that is only hereditary, they have acquired this property by being Hermitian matrices. What are the properties that they are going to get in addition to all these properties as extra properties, because they are positive semi definite? These properties are specific to positive semi definite matrices. Now, suppose lambda is an eigenvalue of A. So, I have a positive semi definite matrix and I consider an eigenvalue of A. We know lambda must be real. Why lambda should be real? Because A is positive definite and therefore, it is Hermitian, and we know that the eigenvalues of Hermitian matrices are real, and therefore, lambda must be real. So, once it is real, either it is positive or it is negative or it is 0. We would like to make some statement about the sign of the eigenvalue. Now, because lambda is an eigenvalue, there exists an eigenvector such that A u equal to lambda u. Now, that says if I now take the inner product with u, I get lambda u comma u. Now, lambda is a constant, it can be pulled out. Now, u comma u cannot be 0 because u is a non-zero vector, and therefore, a non-zero vector inner product with itself will give you length of u squared, and therefore, the length u will not be 0 if u is not 0, and so u is not 0. We will write it this. This norm u squared cannot be 0 because of u being not theta n. So, therefore, we can divide by norm u squared, we get lambda equal to A u by norm u squared. So, the lambda is the ratio of these two quantities, but now since A is positive semi definite, this is the time we are using the property that A is positive semi definite, which is precisely the place where we use the fact that A is positive semi definite. Since A is positive semi definite, the numerator is greater than or equal to 0, because A is positive semi definite, and the denominator is automatically greater than or equal to 0 because the length squared. So, it is a ratio of two non-negative quantities that says that should also be greater than or equal to 0. So, therefore, we have in addition to being the eigenvalue being real, we have the fact that eigenvalue cannot be negative, it has to be non-negative, it is either 0 or positive. So, the conclusion is all the eigenvalues of a positive semi definite matrix must be real and non-negative. Now, 0 can become an eigenvalue only if the null space has non-zero vectors, only if nullity is greater than or equal to 1. So, therefore, we have all the eigenvalues of the positive semi definite matrix are real and non-negative. Now, what are the consequences of this? Suppose again we are all looking at positive, A is always a positive semi definite matrix. So, A has nullity nu A, let us assume it is there is some nullity nu A greater than or equal to. Then what is rank? Rank is rho, and where rho plus nu A is equal to n. Now, what does it mean to say that nullity is nu A? It means lambda equal to 0 is an eigenvalue, lambda equal to 0 is an eigenvalue of multiplicity nu A. A is an n by n matrix, there must be n eigenvalues, nu A of these eigenvalues are 0, 0 appears as an eigenvalue nu A times. Now, how many more eigenvalues we require? We require n minus nu A eigenvalues, which is equal to rho eigenvalues, and since all the eigenvalues are greater than or equal to 0 and 0 has been taken care of here, all the remaining eigenvalues must be positive. All the remaining n minus nu A equal to rho eigenvalues must be strictly positive. Therefore, we can arrange the eigenvalues of a positive semi definite matrix A as an eigenvalue, maybe the next eigenvalue is equal to it and so on. So, there are row eigenvalues which are all strictly positive and the remaining eigenvalues are all equal to 0. So, there are nu A of them. So, nu A of these eigenvalues are 0 and rho of these eigenvalues are positive. So, therefore, if we have a positive semi definite matrix of rank rho, we can always split the eigenvalues into two groups. One group of eigenvalues which are all strictly positive, then the eigenvalue 0. The eigenvalue 0, because nullity is nu A, will appear nu A times and all the other eigenvalues put together will give us rho eigenvalue. In particular, if A is positive definite, then 0 is not an eigenvalue at all eigenvalues are strictly positive. That means, we will have lambda 1 greater than or equal to lambda 2 greater than or equal to up to lambda n, all of them greater than 0. So, the 0 eigenvalue will not appear at all. Now, once we have these eigenvalues, because it is Hermitian, we will be able to find corresponding orthonormal eigenvectors. So, now corresponding to the 0 eigenvalue, we can find, since multiplicity is nu A, we will find nu A I will write it as phi 1 phi 2 phi nu A orthonormal eigenvectors, and since these are eigenvalues corresponding to the eigenvalue 0, forming an orthonormal basis for null space of E. So, the eigenvectors corresponding to the eigenvalue 0 will give us the basis, an orthonormal basis for the null space of A in the case of positive semi definite matrices. Next, corresponding to these positive eigenvalues, we will get eigenvectors say V 1, V 2, V 3, V rho, and they will be orthonormal, because we know that for Hermitian matrices we can always get the orthonormal eigenvector. So, corresponding to the positive eigenvalues lambda 1 greater than or equal to lambda 2 greater than or equal to lambda rho greater than 0, we get orthonormal eigenvectors V 1, V 2, V rho. So, therefore, if A is positive semi definite, so let us summarize this. If A is positive semi definite, all eigenvalues are real, all eigenvalues are greater than or equal to 0, if nullity of A is nu A and rank A is rho A, then I will just write rho here instead of writing subscript. A is rho, then the eigenvalues can be the n eigenvalues. When I say n, we are looking at multiplicities included, can be arranged as lambda 1 greater than or equal to lambda 2 greater than or equal to lambda 3 greater than or equal to lambda rho greater than 0, and then lambda rho plus 1, all these eigenvalues are 0 eigenvalues, and there are nu A of this. And corresponding eigenvectors, orthonormal eigenvectors V 1, V 2, V rho, phi 1, phi 2, phi nu E. Now, these are the basic ingredients that we require to analyze a given matrix. We will see how we can convert all the questions, all the computations that we require regarding answering the questions for a general matrix to those of some simple Hermitian positive semi-definite matrices. Now, let us look at this V 1, V 2, V r, V rho. So, note one important property we are going to observe. This V 1 is an eigenvector corresponding to lambda 1. So, we have A V 1 is lambda 1 V 1, A V 2 is lambda 2 V 2, and there A V rho is lambda rho V rho. Now, note that the lambda 1, lambda 2, lambda rho are all the positive eigenvalues, and therefore, we can divide. So, we get for each V j can be written as A of 1 by lambda j V j, or we can write it as A of x j, which means V j is a vector of the form A of something. So, and therefore, V j belongs to the range of A. This is true for j equal to 1, 2 rho, and therefore, V 1, V 2, V rho belong to range of A. They are orthonormal vectors as we have found in range of A. Therefore, orthonormal vectors in range of A. But what is the range of A? The range of A is the rank, which is rho, and therefore, the dimension of the range of A is rho, and we have found rho orthonormal eigenvectors in that space of dimension rho, and therefore, they form an orthonormal basis for range of rho. So, since dimension of range of A equal to rho, and we have rho orthonormal vectors V 1, V 2, V rho in range of A, these form an orthonormal basis for range of A. So, we get an orthonormal basis for the range of A from the eigenvectors corresponding to the non-zero eigenvalue. So, that is the important conclusion. If A is positive semi-definite, then the orthonormal eigenvectors corresponding to the positive eigenvalues, strictly positive eigenvalues, the positive eigenvalues provide an orthonormal basis for range of A. Now, we have studied Hermitian matrices, we have studied positive semi-definite matrices, which is a special class of Hermitian matrices. We have found some special properties of the eigenvalues and the eigenvectors of positive semi-definite matrices, which we shall again recall. The first property is that all the eigenvalues are real, all the eigenvalues are greater than or equal to 0. If nullity is nu A, the eigenvalues can be arranged in this form, and corresponding to these we will get the eigen vectors corresponding to these eigenvalues. These are orthonormal eigenvectors, and the eigenvectors corresponding to the positive eigenvalues provide us a basis for the range of A. So, now we have studied this special class of positive semi definite matrices. We have seen the notions of vector spaces, we have seen the notion of subspaces, we have seen that any matrix has 4 subspaces associated with it, 2 of them in Rn, 2 of them in Rm. We have seen that these pairs are orthogonally oriented. So, we introduced the notion of orthogonal complements, then we introduced the notion of orthonormal basis, then we had the notion of Hermitian matrices, and then finally, the special class of positive semi definite matrices. Now, we are ready in a position, we have got all the ingredients, all the prerequisites, all the material that we require to analyze a given general m by n matrix, complex or real. Now, we shall put all these ideas together and see how we get all the answers to the fundamental questions that we raised at the beginning of the course. We shall begin this analysis in the next lecture.